Okay, this is ELE 115. We're lecture 3 here when we're reviewing resistive circuits from ELE 110. In resistance, as I mentioned in the last lecture, lecture 2, resistance is an opposition to current flow. And when you apply electrical energy to a resistor, it converts it into heat immediately. That's something you really should memorize. Resistors convert electrical energy into heat energy immediately. All right? That means there's no delay, and therefore, changes in voltage result in immediate changes in current, or changes in current result in immediate changes in voltage. There's no delaying any part of the applied voltage, so there can be no distortion in the circuit. So let's take a look at at a circuit here and go through parallel. We did series last time, series resistive circuits. Let's do parallel resistive circuits. And again, we're reviewing materials. So there's a link in the regular Blackboard site that leads to this guy over here, and there's a circuit here which they solve using Ohm's law. Simple parallel circuits. They have this table method, which is not too shabby. I think that's not a bad way to solve circuits. Well, I don't know what they're doing down here. It looks interesting, but let's take a look at our circuit right here. And the first thing you notice about parallel circuits, there's some rules here. There's only one voltage because there are only two nodes. Node 1, node 2. There's a 24 volt voltage source here, and this voltage source will maintain 24 volts between node 1 and all of this wire stuff here is part of node 1. That's all part of node 1. We lump all the resistance together in these resistance. There's a little bit of resistance in these wires in real life, but in our schematics we pretend that the wires are made of pure unobtainium and that there's no resistance in them whatsoever. So node 1 starts here and goes along, comes all the way down to the start of this resistor, over here down to the start of this resistor, and over here and down to the start of this resistor. Likewise, node 2 starts at the negative side of the power supply and comes down here through this perfect wire with no resistance up to the bottom of R1, over here and up to the bottom of R2, and over here and up to the bottom of R3. Now, let me clean up that little corner there. Oh yeah, it makes all the difference. Okay, so now what we have when we do this is we have conventional current flowing from the positive side of the power supply. So we have a current that comes out here, and some of it will pass through R1, some of it will continue, and then we'll have some that goes through R2, and some of it will continue and go through R3. Okay, and then in each case the current comes down and rejoins. Okay, and this current rejoins here, and the total current flows there. So our total current is I total is right here. All right, and this is this current here is IR1, and here I've got IR2, and this is IR3. It's going to be hard to fit these in here. Should have made things bigger, right? IR3, and this is IR2. Okay, so there's only one voltage. So there's a couple different ways you could solve this circuit. If I want to go with what I call the total resistance method, I have to find the total resistance, and the formula, there are a couple formulas here. R parallel is equal to, this is the master formula that always works, 1 over R1 plus 1 over R2 plus 1 over R3 plus as many resistors as you've got. Okay? Now, when you have two resistors, okay, and you use this formula, you'll find that it reduces to R1 times R2 over R1 plus R2. And this is commonly referred to as product over the sum. All right? And that works for any two resistors. And so that can be a handy way to do things. The other thing we can have is if we have n equal resistors, so we had n equal resistors, each one of this would be, and say their value is R, this would be 1 over R plus 1 over R plus 1 over R. And if there were n of them, we'd wind up down here with 1 over n over R, because these would all have the same denominator. We can add them up, and when you add 1 n times, you get n. So you'd have 1 over the quantity n over R, which, since it's 1 over, we can just invert that, and we get R over n. Okay, great for rules, right? Let's move down here a little bit and let's solve our circuit. So if we want the total resistance in our circuit, our total is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. And you know what? I think we can shorten that a little bit. Save ourselves some room here. And of course that is equal to 1 over 8k ohms plus 1 over 12k ohms plus 1 over 4.8k ohms. All right, so let's bring into play our calculator, and let's try this. I'm going to do 1 divided by, I'm going to say, put a parentheses down here to hold the entire denominator, and then I'm going to put another parentheses. I'm going to say 1 divided by 8. Now they're all k, so I could just say 8, but let's do the right thing here. I'll go second EE3, 8k ohms, end of parentheses, plus the quantity 1 divided by 10. Oops. Ten k ohms. Remember, k is kilo, means 10 to the 3. It means 1,000. So we have that, and then we say plus 1 divided by 4.8 to the third power because it's k ohms. I end those parentheses, and then I end the parentheses for the entire denominator. Okay? And then I hit enter, and I get 2.307k, which doesn't seem right to me. I think because I made a mistake in this thing. Let me go up here, and I think I can edit this. So it's I guess I can't edit it, huh? Let me clear it. Do it again. It's 1 divided by the quantity. 8 to the third power. Isn't it great when the teacher can't even do this stuff? Okay. Plus started quantity 12 times 10 to the third power. Okay. And that plus 4.8 times 10 to the third power. So I end that one, and then I end the entire scheme of things there, the entire denominator. And I'll leave that there for a second in case you want to copy it down. So 8e3 means 8 times 10 to the third. 12e3 means 12 times 10 to the third, and 4.8e3 means 4.8 times 10 to the third. So I hit enter, and this time I forgot to do the 1/overs. Alright, now we're going to save this. I should do it. So it's 1. Right, so for each 1/over, I got to have a parentheses. So it's 1 divided by 8 EE3, boom, plus 1 divided by 12 times 10 to the third. And to that parentheses plus 1 divided by 4.8 times 10 to the third. We end that, and then we put another parenthesis in for the entire denominator. And so here we go. You watch me pull a rabbit out of my hat.
Oh, Bullwinkle, that never works.
This time for sure. There we go. 2.4 k ohms. So we have an answer here, and I'll let you verify that answer. As you can see, I'm really good at doing this. 2.4 k ohms is our total resistance. Well, I got 24 volts. Now I can use Ohm's law to find my total current. You know, my total current. Remember the Ohm's law triangle? It's V, and there's IR in the bottom. So if I want to find I cover up the I, and I see the V over the R, and so I get this equals V total over R total, and that's 24 volts over 2.4 k ohms. So I'm going to have 24 times 10 to the 0 volts over 2.4 times 10. So this is a 0. Sorry about that. Any number to the 0 power is 1, although I would not investigate 0 to the 0 power. That's a little rough, kind of undefined number. And this is going to be 10 to the third because it's k ohms. Okay. And so this is going to be equal 24 divided by 2.4. Well, we know that's 10. And then that's going to be times 10 to the 0 minus, this is a positive 3, and that's going to be amperes, and we're going to get 10 times 10 to the minus 3 amps. And so I total We happen to know that 10 to the minus 3 amps is 1,000th of an ampere, or 1 milliampere. So I total is equal to 10 milliamperes. Okay. And so this guy here is RT. And this is IT. Now, if we want the current through these individual resistors, we can just use this one voltage, 24 volts, because every resistor is between the same two nodes, so every resistor must have the same voltage. So if I want IR1, I can say, well, that's going to be VR1 divided by R1, and VR1, we'll go up and make a little note up here. So VR1 is equal to VR2 is equal to VR3 is equal to V total in this case. All right. So we can rewrite this guy down here and move this down. We can rewrite this guy as V total divided by R1, and that gives us 24 volts divided by 8k ohms, and that's going to be 24 times 10 to the 0 volts divided by 8 times 10 to the 3 ohms, because K is 10 to the 3, and I'm going to get 3, because 24 divided by 8 is 3, 8 times 3 is 24, 3 times 10 to the 0 minus 3 again, amperes, and I'll let you prove to yourself that that's the same. So this is 10 to the minus third amperes is milliamperes. So the answer here is 3 milliamperes. And that's IR1. Likewise, IR2 is equal to VR2 over R2, and that's equal to V total over R2, and that's equal to 24 volts divided by 12 k ohms. And that's equal to 2 milliamperes. Okay? And for the reasons we've shown above, volts divided by K will give you milliamperes. And IR3 will get even more risque here, and we'll just say, well, IR3, it's obviously equal to VR3 over R3, which equals V total over R3, which is equal to 24 volts divided by 4.8 k ohms, and we're going to get that, so let's see, this guy is IR2, put a box around him, and we're going to get that IR3 is equal to, let's bring in our calculator here, and we're going to say 24 divided by 4.8 k ohms, and we're going to get, you can see that it's 5 milliamperes. So this guy is 5 milliamperes, and that's IR3. Okay, and so I'm going to change pages here for a minute. And this will be ELE 115 lecture 2. And this will be page 2 of, I think there's only going to be 2 pages here because we're just doing this parallel circuit. So let's talk about our circuit. We have 24 volts. Give myself a little more room this time. And we have R3, which is 4.8 k ohms. We have R2, which is 12 k ohms. And then we have R1, which is 8 k ohms. And of course we have our 2 nodes here. This is node 1, this is node 2. Some people use letters for nodes. So now I total flows here, and I total flows here too, obviously. Okay. And then I have IR1, and then I have IR2 and IR3. Okay. Now, let's talk about Kirchhoff's current law, often called KCL. All right. In Kirchhoff's current law, you take something like, well, let's take this entire node. Okay. Remember, it goes from here over to here, over to here, over to here. And in this node, there is one current flowing into it, which is IT. And there's IR1, IR2, and IR3 are flowing out of it. And Kirchhoff's current law says the sum of the currents that flow, I guess the best way to say this. So the sum of the currents that flow into and out of a given node will equal 0. Okay? And so we'll say into and out of, And these, we'll let those be positive, and these, we'll let those be negative. Okay? You think about it, if water flows into a pipe, all the water that flows in has to flow out because water is incompressible. And let's not talk about the situation where there's air in the pipe because that's not like electricity. So if you've got some kind of bunch of connected pipes, they're all filled with water or hydraulic fluid or something else that's quote unquote incompressible, then all the water flowing into that network of pipes has to equal all the water flowing out. All right, so if we give those different signs, when we add them up, they have to add up to 0. So what do we have? We have IT that flows into node 1. All right, and so to that we're going to add negative IR1. I'm just being fancy here with the plus negative. We're going to add them all up. That's what sum means. Add them all up. So these guys we're going to call, we're going to make them negative. So yeah, it may seem overly complicated, but this is how it's how I do it. I'm just trying to make a point here. Now this is does this equal 0 or 0 amps, I suppose? And so what I have here, that flows into it, and these guys flow out of node 1. So let's bring over our other paper here. I total is 10 milliamps. And then we're going to have minus IR1, right, which is here 3 milliamps. So I can subtract 3 milliamps, and we could do plus minus and all that, but it's going to come out the same. So then we have IR2, which is 2 milliamps, and IR3 is 5 milliamps. And we all add these all together, and pretty quickly you can see 3 and 2 is 5. You add another 5, that's 10. 10 minus 10 is 0 milliamps. Check. Okay, so that's a way you can tell on these Kirchhoff's current law. I'm sorry, I went down the page. So there's your IT is 10 MA, IR1 minus 3 MA, IR2 we made it into a negative minus 2 MA, and IR3 minus 5 MA. It does add to 0. 3 plus 2, or 3, negative 3 minus 2 is negative 5, minus 5 is negative 10, and 10 and negative 10 cancel out to 0 milliamps, and that checks. All right. So we have, so Kirchhoff's current law has worked. One of the other things we can talk about, I do this so you can see both these things at the same time. So if you look at this part of the node right here, you see IT flows in and IR1 flows out this way, and IR2 and IR3 flow out that way. Well, I've already seen that they all, when you do the whole thing, they all add up. But if you look at this current right here, this current is going to be IT minus IR1. Now IR1 is 3 MA, so you're going to have 7 milliamps flowing here. And that makes sense because this guy flowing down here is 2 milliamperes, and this guy is 5 milliamperes, which is 7 milliamps. So you can use this Kirchhoff's current law, this idea that you can't take more out of a node current-wise than you put in, and you can't stack up current in a node. All the goes intos and all the goes outas have to cancel. The same is true down here on the return trip. Again, this is conventional current, which is not as conventional as we had hoped back in 1800 or whenever they did it. But that's what Kirchhoff's current law does for you. All right, it gives you a conservation of current on nodes, just like Kirchhoff's voltage law in series circuits gave you a conservation of voltage around loops. All right, so you've got Ohm's law, you've got power that we talked about, you've got series circuits and parallel circuits, and you've got web references that refer you to series and parallel circuits in there, as well as the Ohm's law and power information. So we'll cut this one off here. You've seen a parallel circuit done again, and we'll meet up next time, and hope to see you soon. All right, bye.